Z1 plus V1 square by 2G, the three forms of energy, and it will be here at the second point P2 by gamma plus Z2 plus V2 square by 2G, correct, plus HL, because we have the head losses in the system. So let's say the total head loss is HL. Now, if you consider this point 1 here, so what is the pressure, atmospheric pressure? So P1 by gamma here is 0. P1 by gamma, for example, if I write down here, P1 by gamma, that is equal to 0. Clear? Similarly, we have Z1 and we have V1 square by 2G. Clear? Similarly, we have here at this second point here, if you want to write down here, so this will be P2 by gamma in here, plus we have Z2 to account for the losses and plus account for the datum head, and plus we have this V2 square by 2G, the velocity head. So now this will be plus HL, clear? So in this case, you see this will be equal to 0. This V1 square by 2G will be equal to 0 because the velocity here is negligible as compared to the velocity in the pipe flow. That is very small, negligible. So this is 0. Similarly, P2 by gamma is 0 because here again we have atmospheric pressure. And also V2 square by 2G is 0. So this is 0. This is 0 here. These are all 0. So what we are left in the equation? In the equation we are left with Z1 is equal to Z2 plus HL. So what we are left is that Z1, this is equal to Z2. These are different levels, so will not cancel. And plus we have this HL. So now this Z1 minus Z2, it is what? It is your delta Z. So delta Z, Z1 minus Z2 is equal to HL. So this is how this comes, that HL is equal to 36 meter. So now in this case, KE, this is the entrance loss coefficient, this is 0.5, and here the discharge is submerged, so KD is equal to 1. So this is the minor loss coefficient come, and this is what we have. We have this is the major head loss equation. So in this case, the only unknown is V, velocity in the pipe of that of water. It is water is flowing. So now just you solve this equation, the velocity comes out to be 7.53 meter per second. And now you can easily calculate the discharge. Q is equal to A into V, and you get the value. This is 0.6 cubic meter per second. So now discharge is equal to 0.6 cubic meter per second. So this was the first part. The first part they asked that you calculate the flow rate. So now the flow rate, that is 0.6 cubic meter per second. Next, the second part, it is asked that you calculate the pressure in the pipe at 95 meter from the intake. So it says that from this intake here up to this point here, what is the pressure at point P? At this point P, what is the pressure? So next we have to calculate this. And here the elevation is given. This is 39 meter lower than the surface of the water in the upper reservoir. So how we proceed? Now, because the total head loss at P, that will be different, because this HL 36 meter, this is for the entire system. Now we consider only up to this point P here. So we just look to the system up to point P. So up to point P, because it is different than HL, so let us denote this by HL dash. And what will be the losses that we can consider? We have the entrance loss. So you can see that there is entrance to this pipe that we can consider, and because the water is flowing in the pipe, this distance is given, and how much this distance is 95 meter. This distance, that is 95 meter. So that is why we have to consider this major head loss. Now what we do is that this HL dash, that you can easily calculate, since we have calculated all these parameter values, and this HL dash comes out to be 22.89 meter. Now next what we do is we have to calculate the pressure. We have to calculate the pressure at this point. So what we do is that, just like I explained already, we will write down the energy equation between the point at the upper reservoir surface and between the point P. When we write down the equation, this is the equation. So we have P1 by gamma plus Z1 plus V1 square by 2G. This will be equal to P by gamma, that is the pressure at point P, and Z, the elevation of that point, V square by 2G plus HL dash. This is the energy equation that you write down between the point in the first reservoir or reservoir number 1 and point P. So now in this case, when you simplify this equation, so this is the delta Z, which is 39 meter, because it is given that where the elevation is 39 meter lower than the surface of the water. So this P by gamma, this is the pressure head at this point P, and V square by 2G is the velocity head at point P. So that we can calculate, because we already calculated the velocity. This is the velocity here. So this pressure P1 by gamma, this is 0 because it is at the surface. So the pressure is atmospheric in the first reservoir. So that is equal to 0. Similarly, V1 square by 2G, that is equal to 0. Clear? Because the velocity of the fluid in the surface of the reservoir 1, that is very negligible, equal to 0 as compared to velocity of the fluid in the pipe. So it is now easy. So you can calculate the pressure P by gamma, the pressure head, that is 13.22 meter. If you want to calculate in Newton per square meter, just multiply this with the gamma of the fluid. So the pressure, this comes out to be 129.69 Newton per square meter. Okay? So this is how we consider the major and the minor losses in the pipe flow, and we solve the problems. Now next we consider laminar flow in circular pipes. Now in these topics we will try to see how laminar flow occurs in the pipes and what are their characteristics and how to define the velocity profile for laminar and turbulent flow. So first we consider the laminar flow. Now in this diagram what you can see is that we have a velocity profile. In case of laminar flow, we have to see that what type of velocity profile occurs in case of laminar flow. So this is the velocity here, that you can see this is the velocity profile. Now we will use equations to verify that what is the shape of this velocity profile. So now as you can see that when the laminar flow, if you remember, we defined that this is a flow regime in which the fluid particle moves in regular paths, they do not cross each other. So if that is the case, then it means the velocity will be less. When the velocity is less, the Reynolds number should be less in case of laminar flow. So these are the characteristics. Now whenever the flow occurs, let's say in a pipe, so in that case what will happen, that there will be resistance to the flow. So near the pipe wall, at the pipe wall, here greater resistance is offered to the flow, and that resistance is transferred towards the center of the pipe. And due to symmetry, this happens from both sides. So when this resistance is transferred, what will happen? At the pipe wall, the velocity is 0. And this is what we call as no slip condition. And as what will happen, that this resistance will be transferred toward the center of the pipe, and you can see that it will try to slow down the other layers because there will be a momentum transfer, and this frictional resistance, it will be transferred toward the center of the pipe. So that is why you can see that this is how the velocity profile is formed. And if we look at the center of the pipe, so at the center of the pipe we have the maximum velocity, and this is what we call it as denoted by VC, that is the center line velocity, or U maximum, the maximum velocity, because at the center of the pipe minimum resistance occurs to the flow of the fluid. So this is the velocity profile that we will discuss shortly in detail. Now this is what is shown here is the shear stress distribution diagram. So you can see that at the center of the pipe, when the velocity is 0, velocity is maximum, so the shear stress is 0. Clear? The shear stress is 0, and the shear stress increases linearly towards the pipe wall, because at the pipe wall maximum resistance is offered. As a result of that, we have the maximum value of the shear stress. And remember this tau naught, we already discussed, whenever you see the term tau naught, it means that it is the wall shear stress. So this tau naught, this is the wall shear stress, and you can see that we have symmetry in this diagram here, because from this center of the pipe you go up and down. In this diagram we have symmetry. So at this R naught, this is the radius of the pipe, and R is the distance measured from the center of the pipe. Remember, now we will discuss equations, so this should be clear to you. R is the distance from the center of the pipe towards the wall of the pipe. And then we will also use another term which is Y. So remember, Y will be a distance from the pipe wall towards the center. R is the distance from the center of the pipe towards the wall of the pipe. But Y will be a distance that will be measured from the pipe wall towards the center of the pipe. Remember this, because we will use equations, so we should know that R is from the center, R is 0 at the center, and then it is the distance measured from the center towards the pipe wall, and Y is 0 at the pipe wall, and it is the distance measured towards the center of the pipe. So for circular pipes flowing full, we already studied that this hydraulic radius, which is denoted by RH, this is given by R0 by 2. We already studied this. So this formula, if you remember, when we were discussing the major head loss, in that case we derived this equation, that this HF, this is equal to tau naught bar, that is the average shear stress, and we can take it as equal to tau naught because we have symmetry. So this tau naught bar, this is equal to L divided by RH into gamma, the specific weight of the fluid. So if you remember this, we derived this equation while discussing the major head losses. And then what was the problem with this equation at that time? That we don't know how to calculate the shear stress. So then we applied the dimension analysis technique to calculate the value of this shear stress, and then we put here, and then finally what we obtained? We obtained the Darcy-Weisbach formula, FL by D V square by 2G. So that equation that we derived here, so now in RH, you put this RH here in this equation. So what we will get, we will simplify into this factor. Clear? Now in this equation, tau naught, as I said, this is the wall shear stress, and if we proceed in a similar fashion, just like we derived this equation earlier to arrive at the Darcy-Weisbach formula, if we proceed in a similar fashion for a cylindrical fluid body of radius r concentric with the pipe, in that case what we did, we consider tau naught, clear, and we consider on r naught. If we proceed and do the same analysis and we consider in this case now tau and r instead of tau naught and r, so we will get what? We will get this equation. Similar to this equation, we will get this equation. Clear? You will get this equation similar to how we get this equation. But for that equation, we consider tau naught and r naught. But for this equation, we will consider tau and r. So you will get this equation too. This is how this equation comes. Clear? In this equation, what is the difference? The difference is that at a distance of r naught, we have tau naught. Clear? And then at a distance of r, we have tau, the shear stress at any distance r from the center of the pipe. So now when we compare these equations 1 and 2, we get this useful expression. So it means that if the shear stress, the wall shear stress is given, so the radius is normally known to us. So at any distance r, we can calculate this shear stress at any distance r. If you know the wall shear stress, so if you are asked a question to calculate the shear stress at any distance r, this equation you can use to calculate that shear stress. Now we have this expression HF, this is equal to 2 tau naught L by R naught into gamma if we compare this with the Darcy-Weisbach formula. Clear? HF is equal to this quantity, HF is also equal to this according to the Darcy-Weisbach equation. So what we get is that tau naught will be equal to F by 4 rho into V square by 2 or F rho V square by 8. So this is the equation that you can use to calculate the wall shear stress. F rho V square by 8. So this equation is applicable, clear, to laminar flow, also in case of turbulent flow, because this F, it will take care of the flow conditions. So once the tau naught, the wall shear stress is known, that you can put in this equation here to calculate the shear stress at any distance r in the pipe. Now to determine the velocity profile for laminar flow in circular pipes, so we already discussed that for laminar flow, the shear stress, it is given by this equation, Newton's law of viscosity, where mu is the dynamic viscosity and du by dy, this is the velocity gradient. Clear? Also from the previous slide, we have this equation HF is equal to 2 tau L divided by R into gamma. Now what we do is that this shear stress, this value I put here. If you put the value of this shear stress, so now this HF will be equal to this value. Now in this case, what we have is that we have this dy. If I want to replace dy by dr, we have to put a negative sign. This is what I explained in the previous slide. If I go back here, as I said that this r, this is from the center towards the pipe wall, but this y here, it is from the pipe wall towards the center of the pipe. So it means these two distances, they move in opposite direction. So that is why in this case, if I replace dy by dr, we have to put a negative sign. Now from equation 3, if you simplify this equation 3, we get this. Now we have to integrate this equation. because this du, it represents the velocity, and it is given by this equation here. So now what we will do, in this case, what we are doing, that our purpose is to determine the velocity profile. So if you want to plot a velocity profile, that you have to plot with the help of an equation. So now we are looking to derive that equation that we can use to plot the velocity profile. And that equation can tell us that what type of profile we can expect in case of the laminar flow. This is what we are looking right now. So what we do is that we will integrate this equation. This is now in terms of the velocity, we now integrate this equation. So when you integrate this equation, then what will happen? That you will get this as u. So this will become as u, and this is rdr. This whole is constant, so this will remain as it is, and this will be equal to rdr. So integral, so it will be equal to r square by 2. So r square by 2 and 2, this becomes 4. Clear? So you get this. So now you will get u equal to this plus c, where c is constant of integration. When we have indefinite integral, we have constant of integration. To determine the constant of integration c, we apply these boundary conditions. That when r is equal to 0 at the center of the pipe, u is equal to u maximum. We have the maximum velocity. So when you apply these boundary conditions in here, so u becomes u maximum and r is 0. So this c, basically the constant of integration, this is what we get. This is equal to u maximum. This comes out to be u maximum. So this c we put here. This c we put here. And this is how we get this equation. Now we say that let us assume that this factor, this is equal to k, just to simplify this equation. So now if you look to this equation, this is the equation that we get to for the velocity, to calculate the velocity at any distance r from the center of the pipe. So it will be equal to u maximum minus k r square. Clear? So as we move from the center of the pipe towards the wall of the pipe, it is expected that the velocity will reduce. So what we get the idea first. The first idea is that u is equal to u maximum minus k r square. So this is r square. It means that this is an equation of the parabola. As you already know that y is equal to x square. That is the simplest equation of parabola. Y is equal to x square. So same we have the situation here. So this is also an equation representing a parabola. So now what we get, we say that the velocity profile in case of laminar flow is a parabola. Clear? So now we already assume that this factor is equal to k. Now at a pipe wall, what is the situation? That the velocity is 0 and r is equal to r naught. As we saw in the previous slide, you can see here at r naught you have the velocity equal to 0, and at r is equal to 0 we have the maximum velocity. So this u maximum also equal to u vc. Vc is the center line velocity. So when you apply these boundary conditions on this equation here, what we get is that k is equal to u maximum by r naught square. When you apply these conditions, this equation will reduce to this form. K will be equal to u maximum by r naught square, or vc by r naught square. Clear? Now let us proceed. So from equation 4, now k value we determine that this is the k value. Clear? As we apply the boundary condition. So now this will be equal to, u will be equal to vc minus k r square. So when you simplify, this is what you get. So K is equal to this factor here, U maximum by R naught square or VC by R naught square, and it is also equal to this because we assume K to be equal to this factor for simplicity here. Now from here what we see is that VC is equal to U maximum, this is same, this will be equal to this factor here. You just simplify the equation. Now what we do is that we multiply equation 5, this is equation 5, by a differential area dA. This is dA is equal to 2 pi r into dr, and then integrate that equation from r is equal to 0 to r is equal to r naught to find the rate the rate of discharge. Clear? What we do, look to this figure here. In order to calculate the discharge, we consider an area dA. This is the area dA. We have circular pipes, so this is the area dA that we consider. So what is the area here? dA is equal to 2 pi r into dr. So this is the dA, and then the velocity is given here at a distance r. This is the velocity. Clear? So now if we put U into dA, U is coming from here and dA is here, that you put here dA, and then you integrate to calculate the total discharge. So when you simplify, it is a easy integral. When you evaluate, what you will get is that this is the total discharge, pi r naught square by 2 into VC. So now the average velocity that we commonly use in the equations in the problems, that will be equal to the total discharge divided by the flow area. So the total discharge, as we already calculated here, this comes here, and now the total area is pi r naught square. So now what we get, that the average velocity, that is equal to the center line velocity divided by the 2. It means that in case of laminar flow, the center line velocity, that will be equal to twice the average velocity, or the average velocity will be equal to half of the center line velocity. And this is what you can see here. This is what you can see here, shown here in this diagram. So it means that this average velocity here, this is half of the center line velocity. And this is also true. In mathematics, they say that the mean height of a paraboloid is 1/2 of the maximum height. So now we get this equation, V is equal to this factor here given. Now we already know that gamma is equal to rho into G, and kinematic viscosity is equal to dynamic viscosity by the density. So for laminar flow, this HF, if you bring here and you want to calculate, so this HF is now given by this expression. And this expression, this is known as the Hagen-Poiseuille law for laminar flow in tubes. So Hagen was a German engineer, and he developed this equation. And also Poiseuille was a French scientist. He was basically a medical doctor, but in order to understand the flow of blood in the veins, he conducted experiment on smaller tubes with flowing water, and they both developed these equations. So that is why they provide the basic understanding. So this equation is known as the Hagen-Poiseuille law. And the striking feature of this equation is that this is now the HF in case of laminar flow. For laminar flow, we develop this HF. And if you see here, this HF, this is proportional to the first power of V. And this is what we studied in the beginning of this chapter, which shows that the laminar flow, in laminar flow, the loss of head is proportional to the first power of velocity. You remember the diagram when I was explaining HF is proportional to V for laminar flow. So you can see that the theory and experiment, they confirm that in case of laminar flow, the head loss is proportional to the first power of V. So either you use that expression for HF that we use before while solving the problem, or the Moody's chart, or you can use this equation. You will get the same result. And this equation here, you can see there is no friction factor. You see what is involved. The velocity, according to that it comes, we have L, that we can easily determine acceleration due to gravity, diameter, kinematic viscosity. There is no friction factor here, as we see in the Darcy-Weisbach equation. So it means the head loss that we calculate in case of laminar flow, that is due to the viscous forces that are involved. Clear? So the pipe roughness has no effect in case of laminar flow. You have any question, note down in the break time, you can ask. Now comparing the Darcy-Weisbach equation. So for laminar flow, when you compare this HF with the Darcy-Weisbach equation, then in that case you see that you will get this expression, that F is equal to 64R. When you compare this with the Darcy-Weisbach formula, F L by D into V square by 2G, you will get this F is equal to 64 by R. And this is what I said before, that we have derivation for this equation. And this equation you are using in the laminar flow conditions in the pipe to calculate the friction factor, and then that friction factor you use in the Darcy-Weisbach equation to calculate the head loss. Clear? This is how it comes. Now we have entrance conditions in the laminar flow. So let's see that what we have when the fluid enters into the pipe. When the fluid enters, yes.
Kindly previous slide को दोबारा explain करना है, 6 और 7 slide को, उसकी समझ नहीं आई.
What you do not understand in 6th and 7th slide, I already explained. You can watch the video again and again to come into this. I already explained slide number 6, and I also explained slide number 7 in detail. Later on you can watch this video again and again, and if you do not understand, then you can ask a question. Clear? So let us look to these entrance conditions in the laminar flow. So in that case, what we have is that, let's say the water enters into the pipe. So what will happen? Initially, there is no resistance. We are assuming there is no resistance at the moment the water enters, the fluid enters into this pipe. So that's why you can see that here the velocity arrows, they are of uniform magnitude. In this case, they are of uniform magnitude. Clear? What it means that, it means that the fluid here behaves as if it is inviscid, non-viscous fluid. That's why the fluid particles, they move with the same velocity. But as the fluid moves, you can see that there will be resistance to the flow occurs from the pipe wall, from both sides, due to the symmetry. So in that case, what will happen? That resistance, it will be transferred towards the center of the pipe. It will be transferred towards the center of the pipe. And from both sides, what will happen? This is known as the boundary layer that we discussed before, that in boundary layer, the frictional resistance is transferred. Clear? And when these boundary layers merge in some distance L, for example, shown here, this section AB, then you see that the two boundary layers, they merge together. So up to this point here, from the entrance up to this point here, from the entrance of the pipe up to this point here, you can see that the velocity profile is changing. You can see here the velocity profile is changing because the frictional resistance is transferred from the pipe wall toward the center of the pipe. And after this section AB, you can see that the parabolic velocity profile that just we discussed, that is achieved. So that is why we have established flow. that the full parabolic velocity profile that is established. So in the distance where the profile is changing, it's not completely developed, that is what we know as the entrance length and denoted by LE in our textbook. And the flow is unestablished because the parabolic velocity profile that is not fully established. Clear? And after this fully developed parabolic profile is established, then the flow will continue with this profile as long as it is unaffected. Let's say the pipe length is long. After this profile will remain constant. It will not change. But if there is any obstruction comes or flow direction changes or bend occur, then in that case, this profile will change. So this is the concept of entrance condition that we want to see here. And this entrance length LE that we can calculate, that for laminar flow condition, how much will be this entrance length L in which the velocity profile is changing. Clear? So this core here, which you can see here in this core, the fluid behaves as if it is invasive. Clear? But outside that, we have the boundary layer in which the frictional resistance is transferred. So that's why it is known as the invasive core. Now, both theory and observation, they have established that the maximum velocity in the center of the pipe will reach 99% of its ultimate value. You can see here, this one here, the maximum velocity, 99% of its ultimate value in a distance LE is equal to 0.058 times R into D, where R is the Reynolds number and D is the diameter of the pipe. So this equation we can use to calculate this entrance length L in which the velocity profile is changing. If you consider, for example, the maximum critical value for Reynolds number in case of laminar flow is 2000. So if you put this 2000 here and this R, then this LE comes out to be 116 times the pipe diameter. So it means that in this much of length of the pipe, the velocity profile will be changing in the x direction, in the flow direction. And after this, what we will have a fully developed parabolic profile. The flow will be known as established flow. And the fluid will flow with this profile as long as it is undisturbed. Now you can see here in this another diagram, when the fluid enters into the pipe, you see the velocity, these vectors here shown here, the arrows, they are of uniform magnitude. But because the resistance will be offered from the pipe wall, and then this is what the boundary layer will be developed. And this boundary layer will increase in size from both sides due to symmetry, and then they will merge together. And this explains how the resistance is transferred towards the center of the pipe. So when they merge, what we get is that we have a fully developed parabolic profile for that. And this is what we say that it is a fully developed flow. Now the flow after this length LE, the entrance length LE, it will continue with this as long as it is unaffected. If you continue the straight length of this pipe, it will continue with this. The velocity profile will not change. But you can see that when we have a bend, now here the conditions are changing. So you see that the velocity profile is again changed. And now again we have a developing flow. And then after some distance, again it will try to establish the flow. And then the fluid will continue with this profile as long as it is undisturbed. Clear? So in the entrance region that we can calculate, the velocity profile is changing. So what it says is that immediately when the flow enters the pipe, we do not have this fully developed profile, it will take some distance to develop that. So in that entrance length LE, the velocity profile is changing, but after that we have fully developed flow or established flow. Then in that case the velocity profile does not change. It will remain constant. Clear? So that's why as long as the fluid flow occurs in the pipe, for that we have the velocity and the cross-sectional area and the discharge. So that remain the same. Q is equal to AV. That will remain the same. Clear? So velocity profile in the x direction will not change. So it means du by dx in this x direction, we are assuming that will be equal to 0. But this will not be equal to 0 in the entrance region. So the short conclusion is that when, let's say, a fluid enters into a pipe, in case of laminar flow, it will require some distance to travel in order to achieve the full parabolic profile. It will not achieve abruptly this situation that abruptly the resistance transferred from the pipe towards the center and you have a fully established profile. So it is not abruptly possible. It will take some distance to travel and then we have this fully developed parabolic profile in case of laminar flow, and then the fluid will continue. If we have a straight line and there is no disturbance, the fluid will continue with this established parabolic profile till the end. And when there is any obstruction, then it will change because you are changing the conditions of flow. So it will change, but it will try to regain after some distance. Clear? For example, if I show you here, in this case, already the fluid is flowing with a fully developed parabolic profile, but now an obstruction comes in the form of a valve. So in the form of a valve, we are disturbing this. How can it proceed with the same and passing through the valve? So that's why the profile is disturbed, and then again it will travel some distance in order to achieve that full parabolic profile again. Clear? So this is the main idea behind that. Similarly, if we look to the pressure distribution, so we already discussed this in while we were discussing the minor losses. So let's say we do not have this pipe. You already studied in fluid mechanics 1 orifices. So let's say we have an orifice. So what will happen? Let's say we have this orifice here. Or you have the tank. In the tank you have the water. And this is now orifice. So what will happen? That the streamlines, they will come here from all directions. Similarly, straight will come, and similarly from here they comes. And then what will happen? So they are contracting towards this because the flow occurs here in this direction. So what will happen? That just outside this orifice there is a contraction like you see here. Assume we do not have this pipe wall. So what will happen? You will see this, and this is what you see, that maximum contraction occurs here as compared to the diameter of the orifice. And based on that contraction of the streamlines, what we see is that you define the coefficient of contraction, right? Coefficient of velocity, coefficient of contraction, coefficient of discharge. So same is the case here. Like here, in case of orifice, when we have a pipe, because the streamlines are coming from all sides, so they will converge. They will converge here. So at this point, we have maximum contraction and the velocity will be maximum here. At this point, the velocity will be maximum. And then it will diverge to occupy the streamlines, to occupy the full diameter of this pipe. So as a result of this situation here, you see that there will be eddies formation. Pockets of molecules, they will have a swirling effect. Clear? This cannot be air. Remember? So that's why some of the particles, they will have a swirling effect. And this is what we call as eddies. Eddies will form. And this we already discussed in detail when we were discussing the entrance loss, if you remember, in the minor losses. So because of this, what will happen? You have this formation of eddies here, clear, and you have acceleration of velocity here. So because of this, what will happen? The pressure, there will be a drop in the pressure. And because of this situation, what we have is that we have a greater pressure gradient. So you see that there is a non-linear relationship here, because the velocity is changing up to here. After that, once the velocity is established, fully parabolic flow, then we have a linear decline in the pressure because we have head losses. But up to here, since the velocity profile is changing, that's why we have a non-linear relationship. And the factor responsible for that non-linear relationship is acceleration of the core here and the separated flow. So you can see a greater head loss occur here as compared to the head loss here. You see, this is the head loss, this one and then this one. So you can see this one here, and then compare here. This is the head loss. And this we already saw when we were discussing the minor losses. So this is how the pressure distribution occurs along a horizontal pipe. Now, after this, we discuss the turbulent flow, but we will take a 15 minutes break. And then after the break,